Yeah, first we will go with this liquid seal. What this liquid seal means in uh, refrigeration systems. Okay. So let me take a restricted flow passage. Okay. This is a restricted flow passage. Oh, flow passage with a restriction. Or we can call this a kind of metering. Okay. Or metering. It is not about control at the moment, but this is restriction and metering means limiting the flow. Okay, limit. Yeah, we have a little bit signal issues. I'm using now mobile and also the telecom two lines for Wi-Fi. So if one interrupted, I'm using the other. So flow passage with the restriction of metering. Okay, and let's say there is a certain flow trying to pass through this. There is a certain flow trying to pass through this. A certain flow trying to pass through this. So I would say it's a liquid. Okay. Coming in, occupying the full space. Okay. Certain flow trying to pass through this. And it is really have something like a great push towards down. Okay. So as a result, somehow the flow goes out. Flow goes out. So you know that flow comes with the wider area, and let's say this is all in liquid form. Okay, liquid form. So what happens is when this flow passes through this, it is natural to have, we would say it's a bigger pressure drop. You need a high pressure to pass this liquid, okay, down through the restriction. So there is a pressure drop for sure. Okay, there is a pressure drop for sure. There is a pressure drop. There is a pressure drop. Okay, there is a pressure drop. Because it needs a huge force here. After that, it's not necessary to have that force to push through this, unless there is a restriction. Okay, so I would say that unless there is a restriction downstream, okay, downstream, after passing through the flow restriction or through this restricted flow passage. Flow looks eased. Flow looks eased. Okay, means something like a comfortable. Okay, eased with a lesser pressure. A lesser pressure. If downwards, no restrictions. Okay, but the other way here, because of the restriction downstreams, because of the restriction downstream, due to restricted flow passage, upstream flow looks like pressurized. Okay, so you no need formulas for this, but you need very common sense, practical understanding. That is how the nature works. Okay, as a result, there is a pressure drop across the flow restriction. Flow restriction. That is a pressure drop across the flow restriction. And this dropping of pressure, okay, this dropping of pressure takes almost no time. Okay, takes almost no time. So then what happens? Then the phenomena of flashing taken place. Okay, the phenomena of flashing taken place. Okay, so I add here a special word, liquid. Okay, yeah, liquid. That is very important. So then this is liquid seal is very important. Liquid seal means, so there a liquid cell has to be assured. Okay, has to be assured just before reaching the metering or restricted point. Okay, metering or restricted point, the liquid cell. Okay, so for the liquid, this flashing is relevant. If it is vapor, I don't think we should consider any flashing at this time. Okay, but of course there are possibility of sudden increase of the volumes, but when it comes to liquid turn to gas, the volume becomes easily over 1,000 times at low level. I mean that at safety conditions. Okay, at safety conditions. Okay, quite nice. So let me bring some recollections from the previous slides. Bring some recollections from the previous slide of your general understanding about flashing. Okay, general understanding about flashing. This is a previous slide. Okay, this is a previous slide. So I hope you can remember this slide. So I will combine one slide considering these two cases. Okay, considering these two cases. So how to get the space anyway? No big deal. I will take a snapshot of this. So I want you to see a kind of more than similarity, something like exactness. The same thing is taken place. See temperature dropping. Okay, the temperature dropping is taken place. And if I need to add something for this, to make it little complete, there's a portion of gas, a point, and there is a bigger portion of liquid. So no more talking about liquid cells, okay? No more talking about liquid cells. Liquid and some presence of gas, okay, within liquid, presence of gas. So by right, this should be in some bubbles like things, okay. Now make it further small. Yes, something like this. Yeah, that may be too much. Okay, more liquid, but there is a formation of vapor. Okay, then from the previous one, let's see, I will take this 20 degree here, 20 degree, and I will take this 5 degree. Okay, five degree. Yes, exactly the same. Okay, exactly the same. Good. So I have to bring the same to the previous slide. So let me do this way. Yeah, I hope you can understand the similarity of this. Okay, hope you can understand the similarity of this. So you know the importance of flashing. So this is the technique of vapor systems to bring the coldness. Okay, this is the strategy, this is the technique, this is the technology. Okay, so let me bring one more slide here. I have to import this from previous sessions. Sure, looks very silent. Evacuating the gases. Evacuating the vapor form during the flashing. Okay, so repeated evacuation, continuous evacuation is important. Okay, continuous evacuation is important. So this one we are incorporating with this. Okay, we are incorporating this evacuation technique because otherwise there will be limitation of performing continuous generation of cold or continuous removal of heat, in other words. Okay, so we are incorporating this with this solution. Okay, we are incorporating the solution with this basics. So here also for this case, we have to incorporate the same. We have to incorporate the same. So let me take a copy of this slide. Okay, so how to incorporate this? So which means we have to evacuate the gases. This one. Hope you have some memory of this. So we have to incorporate this. Okay, we have to incorporate this. Yes. We need to have this. Okay, we need to have this. Then we can have some continuation. So how we are going to have this is here. First we have to take the vapor, and of course this liquid, we have to let this move through the pipe, okay, for loading. Okay, we have to move the flow through the pipe for loading. It's moving here. Okay, it's moving here for loading. We have little color differences. Previous color looks the same, but anyway, it's okay. Loading. So then the loading will take place. Loading will be taken place. Like this. Okay, once fully loaded, this kind of small bubbles of what? Gases becomes bigger ones, okay? And here, okay, the leaving is full of gas, okay, all 10 because evaporated after energizing. So we have shared this with you, okay? Then we need to take this and evacuate the same way. That's what we call incorporating this solution, okay? So we have to look into the strategy. So we are going for the sucking this and okay, I will take a simple one. Give me a second. So we will take this and we will dispatch. Okay, we will dispatch this. Transport received in gas form and dispatch again. Of course, this energy for the system is provided by this dispatching point. Interesting. So after dispatching, it's going for unloading. It's going for unloading. This is the flow. I just put the flow as some parcels, okay? Flow packets. Okay, this goes for unloading. Interesting. Okay, going for unloading. You will see how the unloading is taken place. Of course, for here, you have to have a component supporting this transport phenomena, okay, for unloading. I think liquid seal is no more the topic is relevant, but this is the beginning of this point, okay? So the condenser is here. Somehow you can see, because of these two components, one is restricting, but the other one provides the power, the energy for the system to move. So combining this, okay, dispatching device and the restricting device, as a result, there can be what? Pressure drops. Okay, pressure drops. And because of the pressure drop, there can be high pressure and low pressure, two sides. Okay, there can be high pressure and low pressure, two sides. Something like here, okay, like this. A high pressure side and a low pressure side. Okay, high pressure side and a low pressure side. Okay, so this is what I need to explain. And I think you all know that at the unloading, this component, okay, this is actually a long pipe with some fins, or it's a long space, okay, it's a space for a flow passage. Loading also, it's a space for a flow passage. Okay, so this is quite okay. I believe this is quite okay for me. Okay, and if you think further, Let's say for air conditioning like applications, if you think of R600A, okay, so loading and unloading, there should be corresponding pressures, okay. Unloading, let's say ambient should be around 30, so you may have something like 45-degree flow of transport. For 45 degrees, this should be around 6 bar. Okay, because it's saturated form, liquid and vapor remains together. Okay, for aircon, for the space, when you are placing this inside the room, this is maybe around 10 degrees C, and pressure is around 2.219 bar. So let me try to make it I'll try to put it here. Should be okay. This is the one. Should be okay. Okay, so there is a pressure drop. See here, from 6 bar to 2 bar. There is a delta P pressure of here. Delta P is 6 minus 2. Okay, 6.1 to 2.2 means it is almost 3.9 bar. 3.9 bar, you may know that it's a huge pressure drop. Not to say huge, but it is a sizable pressure drop. Okay, it's a sizable pressure drop taken place. Okay, within the system because of this metering device. Okay, so you have a pH high pressure and there is a PL low pressure. Let's see if that is the situation, your high pressure and low pressure sides. If this is high pressure, H, P high, okay, is equal to 6.102 bar. 2 bar, P high. Okay, just put this one. Here also P high, same. Here also P high, it's the same. Okay. Here also you will experience the same P high. Okay. Yeah. So here to here all P high. So let me take only P high part. Here also the same, assuming no pressure drops. And in a very good design, you may see no pressure drops. Almost no pressure drops, but practically that pressure drops can be negligible. Here also P high until here P high. Okay. Then here becomes P low. P low, P high, P high, P high. Okay, this P low, here also should be the same P low. Generally, otherwise there can be some performance issues. So you have the P low throughout. Okay, this is again P high. Okay, P high. So you have P high and P low, two sides. Because of these two key components, one is metering, one is dispatching. So when it strikes a balance, this two, there is a pressure drop. But you have to assure there is a liquid set. Okay, liquid set. Till the liquid seal in formation, okay, until the liquid seal is there, the performance of this system is not there because no flashing effect. That's why when you start a cooling system, it takes a little time to feel cold. Okay, at least a little time to start cooling. The reason is this liquid seal formation. Okay, that is very important. Yeah. So that is extra but very useful knowledge to build up this concept up to this levels. Okay. So now I am here plotting the energy levels. So let's say 1 kg packets of flows here. I put all 1 kg packets moving here. Okay, maybe in seconds or in minutes or whatever 1 kg packets I take. So let's say now I have to look into the energy levels. Okay, energy levels. So before that, I will, so let me number. Okay, let me number some specific points. Okay, let me number some specific points here. 1, 2, 3, 4. Okay, 1. I put here 1. Okay, 1 here. I put 2 here. Okay, let me put 3 here. Let me put 4 here. So you can see 4 specific points here. Okay, yeah, 4 specific points. And I think better I should go for a new slide. And I will take for 1 kg now. Okay, 1 kg I will take. 1 kg transport, 1 kg transport. So there are 1 kg packets, so many. Okay, so energy levels. Okay, so when it comes to flowing fluids, okay, so other than the internal energy U, we have other flow works and all. So energies we will put in terms of enthalpies. So I put H1 here. Okay, H1 at 1, H1. Simple means it is for 1 kg. Okay, H2 is here. Then you know H3 is here. H4 is here. Okay, H4 is here. So if you think of 1, it is something like that transport leaving the loading and reaching the dispatch, okay, or the suction side of the compression. 2 means leaving or dispatch, okay, and reaching the unloading. So 2 has a connection for 2 points. Same with 3. So one way it is ending, the other way it's a beginning. So here 3. Here 3. See, 3 2 places. Okay, 3 at 2 places. But when it comes to construction, in between this 3 and 3, in between this 3 and 3, there is a space connected with this system, maybe a piece of pipe. So what to do? So what to do? Yeah. What to do? Same 4 and 4, 4 here. Okay, same 4 here. Maybe, yeah, 4 we can have some anyway, the equal considerations. But there are issues, okay, same like 3 3 3, 2 2, 1 1, 4 4. We have issues, okay. But ideal cases we will take the same at this point of time. Okay, ideal case we will take all same at this point of time. But remember, you cannot be ideal. No? We have to be practical. Yeah, so we have to be practical. We are technologists. Yeah, so technologists are special, you know. They are very special. Yeah, solution providers. technological solution providers. And unfortunately, no one knows the position of technology. That's why you are always going to compare technologists with engineers. That is quite wrong, you know. Engineers are not technologists, technologists are not engineers, but sometimes engineers can be technologists. Sometimes technologists cannot be engineers, but technologists are. They are really quite important stream of professionals. Okay, very important stream of professionals. In Sri Lanka, this is getting established. So per kg, I put all small w's, small q and small values for 1 kg. So that is very important. That's why to become a very good technologist, the first thing is to have a natural understanding of this nature's phenomena. That is number one. Okay, that's why even I'm struggling to explain these things to you. Okay, so you know that even I'm struggling really to explain these things. Otherwise, I can just give a note and I can ask you to go through it. Then my job is done, but I cannot do that because I know the value of technologist and I know what technologist should receive from a lecturer. That's why I'm trying in this way. Okay, otherwise I already passed you the notes. You can go through it. So see the difference. Look for the differences. Okay, don't get compared, but be better and above all. Yeah. So that is what we expect from you. Yeah. Very important. So anyway, that is outside the topic. Since that came to mind, it's okay to mention that as well. So you have 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, but fine at the moment. So we will see this 4 points and high pressures, low pressures. Okay. So interesting. And we are explaining this in numerous ways. So what's ordering of H values? H values. H means energy, values at different points. So which one is the smallest, which one is the biggest? Yes. Of course, you know, after loading, okay, the energy level should be high. So before loading, you have a little less energy levels. After loading, more energized. Dispatching with more power, some more energy in the transport. Okay. But after unloading, this energy level is same like before loading. Why right? Because unloading means energy level should be the same for the loading. So if you order this, it is something like this. I think you can agree, practically you can agree on this. Ordering H values. Are you okay? Ordering H values is in this way. So if you need further, H1, yeah, okay, this is the order. So H1 belongs to low pressure. H1 at P low. So මෙම විනාඩියෙන් ගන්නනේ lecture එකක ඉන්නේ. Okay. So H4 and H3 same energy levels. H1 little high, H2 more high. So H4 and H3. So we can ideally consider this way. So if you need to add an axis for H, if this is the H axis, okay, H axis. Interesting, okay. H1, this level. H2, this level. H3 and H4 at the same level. And I have shared with you about H, and you have to explore further. H. So this is H. Yeah, I hope you can understand this. I hope you can understand this. Okay. Let me duplicate this. And if I add one more axis for this, because we need to consider the pressures as well. So this is your pressure axis. P axis. Enthalpy levels are here. Yes. So you have low pressure, very smaller. This vessel is quite smaller. You have high pressure here. Okay, high pressure. Let me put it more high. Put this more. Yes. H2 at high pressure. Okay. I bring this, sorry. I bring this H1 to this line. Okay. H4 and H3. Sorry. So I have to interchange this. This should be 3 and this should be 4. Okay. Interesting. Okay, interesting. So I'll take a snapshot of this. Oh. Okay, this is the one. Okay, this is the one. So this is our basic pH, because now here under this topic, so I have covered liquid cell and development of this. Now pH diagram for practical usages and also understanding learning 7 points. So we are on that. Okay, we are on that now. Okay, that is pH. We got some lead for this. Understanding pH. Understanding pH. Okay. So you know that this H3 is a liquid cell. Okay. H3 is a liquid cell. So you all looks very silent. Eh? Can you hear at least?
Yes, sir, you can.
Yeah, good.
Yes, sir, we can hear.
Okay, good. Yeah. Let me make it big. It's a liquid cell. Responsibility in between 1 and 2. Oh. Okay. This component here. So it's the same thing that capillaries also doing. It's the same thing. put it here, but this looks, anyway, put the capillary as well, this side, okay. H4 to H1. So this piece is responsible. Okay. Yeah. I think it's a bit, not to say complicated, but it is not that well arranged, but it's okay. Okay. Good. Put this way through this. This is receiver. Okay. Good. W. QH and QL. QL. Okay. W, QH and QL. So you can see the corresponding four major components as well. Okay. So when you all in pH and the liquid cell, liquid cell is here. Okay. Liquid cell is here. Japuta. Okay. Yeah. Anyway, this looks too complicated now. But when you see this video, you will see it clearly. Yeah. Yeah. So before going for 7 points and the professional pH diagram, okay, professional, I would say, yeah. Before that, let me do something. Here, earlier we have done little bit, not to say bit, but some mathematical expressions we have written for QL, W, and QH. So I'm going to remind this to you here. I just put it here. Okay, this is energy balance. QH, yeah, not that clear maybe. This is better. QH, H2 minus H3, because H2 energy level after releasing QH becomes H3 energy level. So QH is what is lost from H2 and become H3. So the difference H2 minus H3 is QH for this case. Same way H1 with the receiving of W becomes H2. So the difference between H2 and H1 is W. So always when you refer a component, okay, example here the condenser unloading, so leaving end enthalpy minus inlet end or receiving end enthalpy. Yeah, should be the way, but here as we put the QH direction this way, we are putting in and out considering the practical points, okay? Considering the practical points, okay? I think it's understandable. W is H2 minus H1 and QL, small ql is H1 minus H4. Remember, don't forget this. Small values we are putting for 1 kg refrigerant or 1 kg transport. Okay, 1 kg transport. Yeah, understand? Good. So now I'm going to redraw this. Okay, what? pH, the same way. Now you have this. pH. So let me draw this in a little better way. Okay. So even though the components are not same, you should know that. This. You should know that the corresponding components are there. Okay. Let me draw this. How to draw? Maybe 2 axes I will take. 2 axes. And I will draw. It is something like quite similar way. Same way, okay? Pressure levels for 10 degrees Celsius and 45. You have high pressure and low pressure, P high and P low. P low here, P high here. Okay? P high and P low. And your H1, H2 H3 and H4. Okay, let me construct it. H4, let's say this is the H4 level. H4 level, yeah, looks straight. H2 level. Put it here. H4 level, I put it here. Then H3 and H4, same level here. Okay, same level here. So let me bring 1, 2, 3, 4. One, 2, 3, 4. It's the same. Okay, I want to draw it a bit better way. That's why I did it. One to 2. 3 and 4. Okay, these two lines, maybe I will change the colors, maybe size. Good. So all the considerations, we have reasons. Okay, nothing came down from a parachute. All we have when one line going off, I'm switching to the other. That's why. So I think this is quite nice. This is quite nice. So let me add something here. 3 is the liquid cell point. 4 has, after flashing, for sure liquid and vapor together. Of course, more liquid, less vapor. Okay, 1 by right should be 100%. Okay, should be 100%. What? Vapor, because for the transport, it should be fully loaded, means it's vapor. And you know that if there is any liquid formation in between, you cannot do this. Vapor compression means brings to the higher levels. Equipment has some issues. Equipment have some issues. You know, you cannot compress liquid from these machines. Liquid is incompressible anyway. Okay, here looks very nice. Good. Yeah, these are the two things I put here. I feel putting this as well. Should put this. Maybe no need to put it, since you know to make this. Not really disappointing with the signals, but no choice for that. Okay. This is the pressure axis. This is energy axis, H. Okay. So I will put maybe as enthalpy. Enthalpy H. So, as usual, remember, this is for 1 kg transport, or means specific levels enthalpy. Or so this pH may be better for you compared to the previous. Okay. Yeah. So I will group this 1, 2, 3, 4. Okay, good. Let me save this. 9 January 2021. S2B2. Yes. Okay. Now I'm going to share with you the screen. I have a reason. This software you can download. This is quite good academic and research purposes. You can use this. There are a lot of data involved. So I'm going to take some standard pH curve. Okay. For refrigerant, let's say we will go for a latest one, R600A. So you have to understand this, but you can see the key axis, pressure here, and here it is enthalpy. So I just selected pH. Okay, have a look on this. This black color line, okay, reminds us a dome shape. Dome dome shape. Here more wide at the bottom means at very low pressures, and it narrows down and finally turns to a tip at very high pressures. This tip point we call the critical point. Above this point, for the properties above this point, all in gas forms. It is impossible to have liquid, okay? 100% gas. So this is for R600A. So you can see this dome. You can see this dome. I have a purpose to take this. I have a purpose to take this. So let me copy this. So I'm sharing the screen now. Let me copy this. R608 enthalpies. These are very standard So this is a very good resourceful software, this cool pack. New slide. I paste this. Too big. Okay. So whenever, so in our application, we have to take this first. Okay. And then we have to outline the pressures, high and low pressures afterward. So these are the pressure lines. You cannot see it. So I will make it. Yes, now you can see. Line style. Let me make it continuous. Okay, so these are the high pressure line. Of course, I'm not referring the exact values. And the low pressure lines. No idea, but I just put here. I'm not referring the exact values. Okay. So let me mark the point 3. Because in a design, we have to assure the liquid cell. Let's say here it is 0.3. This is 0.3. Okay. And straight down here. Okay. Three and 4, as you remember. This one. Okay. So remember this. I'm drawing this. Okay. Yeah. So your 0.4 will be here. Okay. Then after all becoming vapor, your 0.1, because we cannot guarantee exactly this is only 100% saturated, so there can be little extra superheat of this. So let's say 1 is here. I just put 1 here. Okay, 1. Even 1 is a point we should define. So 4 is automatic. These two lines, the pressure lines, we should define well. Okay. Pressure lines we should define well. Okay, good. Then, based on this, we know the compressors. From the performance point of view, we can see, of course, if it's a constant entropy line, this I believe this is the entropy line. Isentropic, this moves like this. So your point 2 will be here. Point 2. Actually, in the Zoom sessions, I am working, you are just watching, watching. You are something like a spectator. So by that you should work and I should instruct only. But now we have to do everything for you. So at least you should have a good focus. So this is 1, 2, 3, 4 points here. Hope you can understand. Okay, hope you can understand this. So 4 points. Where are the 7 points? Where are the 7 points? I will put the other points. I put 1 point here. 5. 6. Okay. 5, 6. And if you need the 7th one, I will put it here. Okay, so these are the 7 points. And 1, 2, 3, 4 is quite clearer for you. Okay. 1, 2, 3, 4 are quite clearer. Okay. And the other points, I denote as 1 dash, 2 dash, and this is 3 dash. Point 3 should be here because liquid cell. So we have to assure this is liquid. That's why we have to have a general understanding of this properties. Okay, here as charts. Okay, on this we are plotting the diagrams. So pH chart is one thing, pH diagram is one we are plotting on the chart. Okay, is what we are plotting on the chart. So we have done the 7 points as well. Okay, so this is not complete yet. Okay, this is not complete yet. We have 15 minutes. We have 11 students, including myself. So only 11 together. Yeah. So this is very important. And then here, three and 3 dash. Okay. This is important design parameter. I just put it there. Later I need to explain this. Actually, we could have discussed this in much better ways, but we have the timing issues. This too also. We have to be mindful in the designs. Okay. So this one also I mentioned here. Later we will know what these are. And naturally, even between 2 and 2 dash also we have to mark that a bit. So let me mark it. At least to say it more prominently. Yeah. Good. So these are the 4 points. Sorry, 7 points. Okay, these are the 7 points. And I believe you have some understanding about this. 7 points. And any questions before going for the next section, Buddha? Any questions? Do you understand this? Ruben Tirnad, Paris? Very good.
Yes, sir.
Thank you.
Everyone,
Okay.
sir.
Very good. So let me continue this. So I'm going to share the screen with you. Screen, I have a purpose for that. So this is the graph, pH graph, and I'm going to draw a circle now, cycle. There you will understand the rest. So this, let's say this is a cycle name, R600D. So these are very practical purposes, R600D. Understanding transport, I just put in refrigeration. Let's see what this software is doing. Okay. it's asking for evaporating temperature. This is the heat loading. Then the component temperature, the transport. 10, we got 10 because pressure is 2 point something. Condensing, unloading, we put 45. So I'm putting the same. Okay. So here subcooling means for the liquid cell. We have to assure that a sufficient, means it is just maybe below the critical point. So I just put 5. Okay. Subcooling. Superheat is there because to assure the gas is moving through the compressor for compression. I put 5. Okay. Pressure drop evaporator DPI, I make it 0 because it has no limitation or no restriction for the fluid. Because if restrictions, there should be flashing in the evaporators. So all the pressure drops are 0. Efficiency of the compression, isentropic efficiency, I have shared with you, I put it as 1. So these are the conditions. So I'm going to copy this. Okay. Copy this. And I will put into your notes here as this. Design consideration for cycles inputs. So after cycle analysis, you are going for the component developments. So back to this. So now I click update and I ask to draw the cycle. See, this one exactly like what we have done. So I'm going to copy entire, maybe here. That's why I would say we are learning something professional. Yeah. I hope you can see the cycle. Okay, I hope you can see the cycle. So here, whatever we draw here, also let me take that. I just take a snapshot of this. I take this. May I take the complete one? See, it is quite similar. See, it is quite similar. Okay, so you can feel it better. So this is basic the things you have to have when you do this analysis. So this is quite similar. So we have to do the analysis as well, but before analysis, I have to mention something for you. this line. Okay, so you have all the same 1, 2, 3, 4, and then 1 dash, 2 dash, 3 dash, and 4 dash, and the corresponding component. So 1 is mentioned here very well. Okay, reaching the dispatching. 2 as well. So additional 1 dash means the ideal point of 1. Okay, transport turned into saturated vapor, x equals 1. That's the ideal point of 1. Okay, generally we don't go for ideal because in practice we have to have safety factors, and also we are going for extra. That's why 1 is the actual, 1 dash is the ideal. 3 dash point is the limiting point of 3. This is the number 3 point. Limiting point of 3. Entering the metering device. This 3 dash. For 3 dash corresponding is 4 dash. But for actual 3, it's a 4 after leaving the metering device. So you know that 1, 2, 3, 4 are conditions entering and leaving major processes connected in the cycle. Okay, so this is how we should consider the 7 points. The 7 points. Understand? Yes. I believe you can understand this. So this is considered the master slide, and hope you can look into this. Not finished yet, but it is 3:30. Any chance to get extra 5-10 minutes for us to complete this? Any chance to get Putta? Because here we draw the cycle, true. We draw the curve. This is the one, and we have to get the yes, this is the corresponding data.
Yes, we can do.
Sorry. Okay, very good. Yeah. Where is that graph? So we will select the curve. Nice. Show info. These are the information. Now I'm going to copy this information. Okay. Copy. So what I will do is I will copy this way. Because we are going to analyze this. And we have to get the coordinate points, the values of the points. This is the one. Values. That is this. go for the screen maybe. Yes, values. So I have to get the values also copied. These are the values. Give me a second to analyze this. You have to do the same afterward. Yes. Good. Okay, so these are the points. So we will look into the curve now. We will look into the curve 1, 2, 3, 4, and all. So okay. I hope you can remember the expressions. There are the expressions we got for here. So I will do the analysis based on this, because these have some practical relevances. Okay. So now I'm going to calculate QH. QH is QC in this results. Okay, QH seems QC. Is unloading. Okay, QH is unloading. So unloading is H2 minus H3 in our case. So here we have to look for the values. H2 is, of course, should be the highest H value. So highest here with the highest pressures. So if you see here, you can see 617.134 at 6.102 bar, 45 degrees Celsius. But when you generate, this is 45.313. That's how this software works. So 45 become 45.3 because of this. Maybe some incremental values. That's how it is. So we have 617.134 as H2. Okay, this is H2. Kilojoule per kilogram per Kelvin. Okay, minus H2 minus H3. So H3 means the lowest energy level or enthalpy at the same pressure. Your high pressure 6.102, you have C 295.182. So that is our case H3 294.182. So that data point is different, but our naming is different. So H2 minus H3 becomes, this is 321.952. Okay, I'm just using the data. So then W is H2 minus H1. H2 minus H1. These are little smaller fonts.
Sir, excuse me, sir. Excuse me, sir.
Yeah, Buddha.
Sir, how come H3 is H3 value?
Sorry, Buddha.
H3 value?
H3 value. Yeah, H3, this point number 3, here point 1, 2, 3, 4, there are little differences because they are considering 15 points. Okay, so these points are different. Let's say example, if I show you, okay, if I show you, we have 15 points, see? So 1, 2, 3, okay, 4, 5, 6, okay. So our H3 is H4 in this case. Understand, Buddha? So we are considering only 7 points, not the 15 points. Yeah, okay, I have to share the screen. So this is from the software. You can see 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here 8 points are here. So our H3 here, it is H4. Okay, oh sorry, yeah, H5. Here it is H5. Okay, it is something like that. H6 is our H4. 5 and 6. So let me show you now our results. Don't worry. So see H5. 295. Okay. And H4 is 295. So for this case, so H2 minus H3 means H3 is 294. So 294 here at high pressure. Yeah. Okay. Let's see. Here you can see H4 is 295 at high pressure. So our case H3 is, in the software, this is H4. Okay. In the software, it is H4 software. Soft. Okay. That's it. So that's why H4 software is 294. See, 295 point at high pressure. So W is H2 minus H1. Ours and software, it is the same. Putha, can you understand? Can you understand now the question? Did I?
Okay, sir. Okay.
Yeah. So that's why. So you have to be specific. You have to watchful on the points, because this is software. I'm just showing you. Software point numbering is different, but we should pick the right numbers for us, for our case. Example, yeah, later I will explain it further. So W is H2 minus H1. So this case H2 minus H1 is,
Yes.
okay, Bhutan.
Yes, sir.
Okay, good. So W is, H2 is the same.
Sir,
Yeah, Bhutan.
sir, excuse me, sir.
Sorry?
Sir, 295. Sir,
295.
sir, excuse me, sir.
Sorry, 295. Again. Yes, again, Puta. Okay.
Sir, can you share the screen? Okay, sir.
Okay,
It's
295.
three.
See 295 here. See, this is 295.
It's above.
Okay, this is
H3
295.
is 294.
No, Puta, here for
Above.
this case, you can see from the data here, this is 295. Okay. From the data, I'm taking from the data here, this table. See here 295. See 295 here.
Sir, H4 soft.
H4.
Sir, upper.
Yeah, H4 is at in the
H4
software.
soft and
H5 soft.
294 is there.
Where is 294? It is 295.182.
H2 equal 617.134 is there, sir? 2945.
295.134. Sorry,
Yes, sir.
295.182. Yes, okay. Thank you. 295.182. Okay. So that is H3,
Okay,
H4
sir.
soft. Okay, thank you. So here 295.182. So you have a value, right? So H2 minus H1. So it's the same, 617577 with decimal. So this is this. Okay. Now you see COP or even the QE evaporate. QE. I have to make it a little bit bigger. Yeah. QE loading now. Okay, QE loading. Loading. So loading is Q1, sorry, H1 minus H for our case. Okay, H4 is in the soft. It is H5. Okay. So 577 minus 295. See? So this is 282. So what I want to show you is, you have this data, QE value, you have W and QC from the data, W. So all for 1 kg, per kg you can say it. All for 1 kg transport. Then your COP means something like efficiency or the effectiveness. Effectiveness is 282 this divided by the work 39. Okay, so this should be your COP. So if you calculate this, you can get a certain value of COP. So that is 7.140. I'm calculating here. 7.140. So this is the value. Okay. And now you see the results here, output calculated. So I'm taking from here. See the data here. I'm taking here. Packing kata karanne. Hello. Hello. Packing kata karanne. See, but all looks the same. Okay, all looks the same. See, QE is 282. QE is 282. QC is 321. 321. Give me a second. So can you see these values, Puta? So this is how this software evaluations same like what we can calculate from the data. So now we are merging with the practical points of view. We have used the software, plot the points, and we have done something like theoretical analysis with the software application. Results looks the same. And one more I have to share with you here. Let's see energy balance. Energy balance. So energy balance means QL plus W should be, sorry, QE plus W should be QC. QE plus W. So QE, okay? QE means 284, okay? Plus W, 39.5. See the value? Okay, see the value. If you can convert this, so let me open up the calculator. Calculator is here. 282.4. 282.4. 4 plus, okay, plus, I don't know how to put the plus sign here. Anyway, I will copy this. I can copy this. Total is 3 to 1.952. What is 3 to 1? See, you can see that is QC. Okay, that is exactly QC value. Okay, see here the QC value. That is exactly QC. So you have learned a lot here, and now this looks very simple for you if I'm not mistaken. Okay, this looks very simple for you. Yeah, 7 students are here. So here, if you look into this, we have done today understanding flashing and liquid seal. 7 points we have done an understanding and analysis of pH diagrams for practical usages. We have done that as well. So we can do some analysis also afterward. Then next session we have to start how to look into the TS diagrams. So immediately after that, refrigeration system analysis we can do for very reasonable practical levels, and later for steam power plants it's a matter of only 1 day, because this kind of cycle with transport you have already learned this. Okay, so the balance is very simple. Okay, so that's all, Putana. Thank you for being with the class for so long. Paris as usual, and Ruben also here. Thank you, Putala, all of you. Hasita, yeah, all there. Yashoda
Yes, thank you,
and
sir.
Azim, all, thank you very much. So let me upload this record. Record means a video. If you can really understand this to the fullest, beyond that, it is really a remarkable achievement. That's why I have to share this in this way, so that there is nothing to memorize, nothing to forget. You know something naturally. Yeah, because it's a natural understanding with some data and analysis. So it's a blend of the practical and the theory and imaginations and all. And it's for us to move forward afterward. And especially I have shared with you the flashing, like the very important phenomena. So our timing is limited. If not, I can share more with you, but at this point of time, we will be contented with this sharing. So next week we will be learning TS and some analysis, and we will go for power plants. Okay, very good. Then I will send you an assignment about heat pipes. I have not sent it yet. That is outside this, but in your notes you can see the heat pipes, because we have to see something practical out of you, really. We have to see something practical out of you. Yeah. Calculation kande the velawakata wadak naha. But of course we need calculation, but we need the fundamental and the creativity and the technology based. Whatever assisting calculation is okay, but totally doing this questioning and answering with calculations and formulas, it will not bring you the necessary, the relevant and the valuable knowledge. So our approach is a little bit unique in the sense, and I would say you all are lucky enough if you can pick up this. And remember, thermodynamics engineers, thermal engineers are very rare in Sri Lanka. Thermal technologists are very rare. So if you can pick up this subject very well, every time you have the opportunities, the more you experience, the more you have the opportunities. You can develop wonderful things. Yeah. So that's a chance you are having with this tangible knowledge. So that's all for today, Bhutala. Thank you very much for joining with the class. If possible, arrange extra session if possible. So I know that Priyanta is busy and Hasita also going to be busy in the coming weeks, but anyway, if try to find some time should be very good. So that's all. Thank you very much once again. So let me stop the class. Bye then, Putana. Bye. Bye.
Thank you, sir.
Bye.
Thank you.
Thank you, sir.
Bye.
Thank you, sir.
Bye. Bye, Putana. Bye.
Thank you, sir.
Okay,
Thank you,
Putana.
sir.
Bye. Take care, all of you. Bye.